Good afternoon and welcome to the American Floral Endowment's Grow Pro webinar series. I am your moderator, Dr. Haramrit Gill. I am a member of AFE's Young Professional Council and Environmental Horticulture Advisor at University of California, Agriculture and Natural Resources. I have a master's in horticulture from Punjab Agriculture University in India, and I recently completed my PhD in horticulture from Texas A&M University. Today's session is on preventing undesirable purple coloration on cuttings propagated under LEDs. On behalf of the endowment, I'm excited to be part of AFE's Grow Pro webinar series that features a new topic every month presented by an industry expert. The webinars are free to everyone thanks to the generous support of AFE sponsors. The views and opinions expressed in these webinars are those of speakers and do not necessarily reflect the views or positions of AFE. As an independent nonprofit, AFE cannot endorse any specific product or opinion. Today's webinar is sponsored by Smithers OSS. Smithers is a diverse global manufacturer and marketer of floral foam and design media, floral design tools and accessories, post-harvest products, cellular growing media, temperature control packaging, and custom foams for specialized applications. If you'd like to learn more about our sponsors or are interested in becoming a sponsor for a topic, you can find the information on AFE's website at endowment.org/growpro. The link is pasted in the chat. Today's session was pre-recorded in English by Dr. Roberto Lopez. After the presentation, Dr. Lopez will join us for Q&A. Feel free to submit your questions through the Q&A feature and chat at any time. We'll answer as many as we can before the end of the hour. Unanswered questions may be answered through a separate email exchange. This session is being recorded and will be shared to AFE's YouTube account. Through YouTube's accessibility features, you can access closed captions in other languages. To get us started, I would like to share a bit about today's expert speaker. So Dr. Roberto Lopez is an associate professor and controlled environmental floriculture extension specialist at Michigan State University. His research focuses on propagation and production of young and finished plants in greenhouses, growth rooms, containers, warehouse-based plant factories, and vertical farms. The primary objective of his research is to determine how light substrate and air temperature and carbon dioxide in controlled environment production influences crop timing, rooting, yield, quality, flavor, nutrition, and subsequent performance. Dr. Lopez, welcome and thank you for presenting today on preventing undesirable purple coloration on cuttings propagated under LEDs.
Well, thank you very much for that introduction. So my name is Roberto Lopez, as was previously mentioned, and what I'm going to talk to you today about is preventing undesirable purple coloration on cuttings propagated under LEDs. We're going to first start off, though, by looking at our end goal. What is it that we're trying to produce in terms of a young plant? So I've got three examples here. On the left, we have a young plant that meets a few of the criteria we're looking for, right? So it's compact and it's vegetative. But when we look at that root mass, it's really not well-rooted, as well as the stem caliper, although it's pretty difficult to see in this photograph, it's pretty thin. Now let's look at the picture right below. Again, this one meets two of the four criteria that we're looking for. It has fully rooted liner, right? We can see all of those roots. It also has a large stem caliper, but it's not very compact, and that liner is in flower. So now let's look at what we're ultimately going for, right? A compact, fully rooted, vegetative, and strong stem caliper so that it can withstand mechanical transplant as well as even shipping. So what are the environmental parameters that we look for during young plant propagation? Well, typically we want to maintain our air temperatures between 73 to 77 degrees Fahrenheit. We want to try to maintain a root zone temperature that is similar or slightly warmer than the air. I know that not all growers have this capability. So if you don't have that capability, you're going to want to stay on the warmer side of the air temperature range. You want to maintain a vapor pressure deficit of around 0.3 kilopascals. And as you progress through propagation, you're going to want to increase that vapor pressure deficit. One really important thing to remember is that we want very little to no air movement, because that's going to dry out those cuttings. And then what we're really going to focus on today is that daily light integral, or the cumulative amount of light that those cuttings are receiving over time. So initially during stages 1 and 2, we're going to want to have relatively low light levels, and then we're going to increase them during stages 3 and 4. Let's first off, let's talk about light, because again, that's what we're going to be focusing on in this webinar. So in terms of light, there are, it says here 3 dimensions, but really there are 4 dimensions of light for plants. Today, we're going to focus primarily on that photon flux density, which is going to influence plant biomass as well as rooting and other parameters. The spectrum of light, which again is also important, and we'll briefly talk about that today, is going to affect the morphology, right? So it's going to affect the size of the plant and even the color. And then there's the photoperiod, which is typically going to affect flowering. One aspect that we often tend to forget is that with all of these parameters, that light uniformity is very important. Another important thing to remember is that all of these parameters or dimensions of light interact with one another to affect, again, the plant biomass, morphology, and flower, and which is ultimately going to affect the growth and development of those plants. When it comes to that instantaneous light that our plants are receiving, we typically talk about the photosynthetic photon flux density, or PPFD. And what we're talking about are the photons of light that are used in photosynthesis, which are between 400 to 700 nanometers. And we are most interested in how many of these photons are falling within 1 square meter. So the units that we use are micromoles per meter squared per second. Again, something a little bit different than maybe some of you are accustomed to in terms of light. And we need to think about the cumulative amount of light that a plant's going to receive over the course of the day. So here we use this term called the daily light integral, or DLI. Again, it's the cumulative amount of photons that are within that par range from 400 to 700 nanometers that are falling within 1 square meter. But the units here are moles per meter squared per day. So if you remember previously with the instantaneous, it was micromoles per meter squared per second. But again, here it's over the course of a 24 period. So when we think about daily light integral, here's a map of part of Michigan. And in Michigan, we have very low daily light integrals, and we end up having to use supplemental lighting for that reason. So if we look at January, December, January, February, March, you can see that these are the outdoor daily light integrals. They are quite low, especially here in Southwest Michigan, such as in Kalamazoo. Now, how does that equate to within a greenhouse? So these are maps that you can download here on the AFE website. These were developed by Jim Faust and his colleagues. And here what we've done is we've slightly modified the numbers to show you what the typical greenhouse DLI is, right? So when we move from outside into a greenhouse, we are seeing a pretty drastic reduction in light transmission depending on the glazing material, the superstructure, as well as any hanging baskets that you may have. So you can see that in the winter, right around December, our daily light integrals are quite low, especially in northern latitudes. As the season progresses, you can see that within the greenhouse, those daily light integrals start to increase. And by March, we have much higher light intensities that are reaching our crops. Okay, so here's when that supplemental lighting comes in, right? Again, it's going to be important to use that supplemental lighting on cloudy days and during the night, right? Because we want to make sure that our plants are receiving enough photosynthetic light so that they can grow, and especially for young plants, that we can get roots on them and get them out as quickly as possible. So one really important thing to remember is that there are differences between photoperiodic lighting and supplemental lighting. So these are the fixtures that we typically use for photoperiodic lighting. They're typically going to be screw-in bulbs. Again, very low intensity, typically going to provide anywhere from 1 to 2 micromoles of light. This is, again, so that the plant perceives a long day. And again, the spectrum is typically red and far red light or white LEDs, and we're going to use them for about 4 hours a day. So again, this is not what we're interested in this particular webinar. What we're interested in is that supplemental lighting. It's going to be high intensity light, anywhere from 50 to 100 micromoles per meter squared per second. And this is what's going to help us, again, in terms of rooting, increasing those plant quality attributes. Now, the only really fixtures that are going to be efficient and provide such high light intensities are going to be high pressure sodium lamps, as we have here, or LED fixtures. Again, we're going to use them at night or on cloudy days, and we're going to run them, anywhere from a few hours up to about 20 hours a day. So here's an important table showing you, let's say that you have a supplemental lighting fixture, and it provides 75 micromoles of light at plant height. And let's say that you run those lights for 16 hours. So if we go here, 75 and 16, we are providing an additional 4.3 moles of light. Now, if we were running a fixture that, again, let's say was providing 150 micromoles, right? And we ran it for 16 hours. Again, it's double the amount of light, so we're going to get double the amount of, increase our DLI by 8.6 moles. But typically in propagation, as I mentioned before, between 50 to 100 micromoles of light is sufficient for given plant production. And here's some work that we did here at Michigan State many years ago, looking at the influence of daily light integral on the rooting of New Guinean patients. So these are the conditions that we would receive in Michigan during the winter, anywhere from 1 to, let's say, 5 moles of light, depending on the location. So very, very low, right? This is no supplemental lighting. And this is after 16 days. But when we provide supplemental light, look at how many more roots we have. We have more leaves that have unfolded. But more importantly, we find that when we provide supplemental lighting, we can root these cuttings in under 2 weeks. Well, when we have very low light conditions, it could take us anywhere from 5 to 6 weeks to root that crop. So even though we're spending money on that supplemental lighting, we're reducing the overall propagation time, which is ultimately going to save us a lot more, and we're going to be able to have more turns in that greenhouse. Here's an example with seedlings. So here we have dianthus, and again, daily light integrals from 4 all the way up to 19 moles of light. 19 moles is going to be pretty difficult to achieve, especially in the northern latitude. But what we find is by increasing that daily light integral, we see that the shoot dry mass, so again, this above ground biomass, the vegetative part, increases quite a bit, as well as that root dry mass, where we see nearly a 4-fold increase in root dry mass as we go from 4 to 19 moles of light. Again, here's another study with petunia seedlings where in this scenario, we wanted to see if, let's say, a grower just doesn't have enough supplemental lighting fixtures to provide light during the entire propagation stage. So what we're seeing here is, again, this gray box represents low intensity lighting. So again, just to provide photo period. And the yellow box represents high intensity lighting from an HPS lamp at 90 microdose. So what we can see here is that with this seedling, it was grown again under very low light conditions throughout the first third, second third, and throughout production. So we can see it's not very well developed, has few roots. When we provide supplemental lighting initially, in the middle, or at the end, we see that it's more beneficial right in the middle or at the end than at the beginning, the first 9 days. And what happens if we provide supplemental light, either for 2/3 of production. Well, we can see that when we provide it in the middle and at the end, we have a much higher quality young plant. And obviously, as we would expect, if we light throughout, we're going to have the highest quality. Again, this is showing you, again, if you don't have the capability of providing light throughout the entire propagation stage. Okay, so here comes the big question that we often receive is, should I utilize a high pressure sodium lamp or an LED supplemental lighting fixture? Well, if you are located in a northern latitude and the daily light integral that you receive from the sun is less than 8 moles per meter squared per day, then that light spectrum from the LEDs may have an effect on stem elongation, meaning that those cuttings or seedlings might be more compact. You're going to see a reduced leaf size and sometimes an increase in leaf coloration. However, when the daily light integral is higher than 8 moles, you're typically not going to see much of a difference between utilizing an HPS lamp or an LED. So here's an example. Here we have petunia that was grown under, again, very low light Michigan conditions, where our solar daily light integral was anywhere from 4 to 5 moles. And here we have our high pressure sodium lamp, and here we have our LEDs. And what's the biggest difference that you can see? There's virtually no difference in terms of rooting, but look at how much smaller and more compact those seedlings are under the LEDs versus under the high pressure sodium. So again, this is one potential benefit, is that you may not necessarily have to use the plant growth regulator. Okay, well, probably of more importance is the energy efficiency as well as the output of those fixtures, right? Because that's ultimately what's going to affect your energy costs. So one thing that we need to know is how much light intensity, how much light in terms of the photosynthetic photon flux is that fixture providing, right? We need to go back to some of the initial slides that we looked at, and we're most interested in 400 to 700 nanometers, which is that photosynthetically active radiation. Another important parameter is the photosynthetic photon efficiency. So this is basically talking about how we are converting electricity into light that the plant can utilize for photosynthesis. So here's some information, and again, this information is always changing because the efficiency of especially of LED fixtures is increasing each year. But here's just some examples showing you the photosynthetic photon flux of various high pressure sodium lamps on the market. So we can see that it ranges quite a bit, right? From a 400 watt fixture all the way up to a 1,000-watt fixture, where the photosynthetic photon flux increases from 400 to over 1,800 micromoles per second. Now, let's look at that photosynthetic photon efficiency. Again, the efficiency of those fixtures at converting electricity into light. So we nearly double the efficiency as we go from a 400 to a 1,000-watt fixture. Now let's look at LEDs. We can see that with LEDs, the efficacy is well over 2 and all the way up into the 3 range. So again, this shows you that LEDs are much more energy efficient than high pressure sodium. Okay, what are other things to consider when deciding if you might switch from HPS to LEDs, or we're going to install supplemental lighting for the first time? Well, obviously you're going to consider the costs, right? So purchasing those fixtures, as well as the installation costs and any energy rebates that you may receive. So many utility companies will provide rebates for installing LEDs, either retrofitting from HPS to LED, or there are also rebates through the government. Another obviously important thing that we talked about earlier is the energy efficiency, the longevity of those fixtures, as well as any potential maintenance, right? So with HPS, there are some maintenance things that you got to consider. You also got to consider how with an HPS, the number of times that you turn them on and off is going to affect the lifespan of that lamp. With HPS lamps, plant temperature is generally going to be warmer, right? Because they produce a lot of radiant heat, as well as you need to consider any effects on plant morphology. Okay, so now this leads us really into the webinar and what we're going to focus on. So over the past several years, many young plant producers have installed LEDs, right? Because of the factors that we just mentioned, but primarily that energy efficiency. Now, unfortunately, one of the things that many growers started to notice is the development of this purpling as well as chlorosis on the leaves of certain species, such as petunia. And again, we had never seen this in the many years of research that we had conducted here at Michigan State. And so when we started hearing these reports, it was actually quite, surprising to us. So we started to look at what could be potentially causing these issues. Could it be the intensity of light or the quality of light from those fixtures? Could it be temperature, right? As I mentioned before, plant temperature is going to be lower under LEDs than it is under high pressure sodium. Or is it that the plants are developing very quickly and there's some sort of nutrient deficiency occurring? So again, lots of different questions. And again, we still haven't answered all of these questions, and we're hoping to do some more research in this area in the near future. But again, these are photographs that we received as well as that we took visiting young plant producers across the US. So again, the symptoms varied, but in most instances we saw purpling, whether it was interveinal, we saw yellowing, or purpling of the entire leaf. Again, is this reducing the quality of the plant? Well, if you're a young plant producer and you're shipping this material to another grower, the other grower is not going to be happy, right? When they've spent quite a bit of money on this liner tray and it's yellow, purple, and not the highest quality. Yes, they have roots on them. They're nice and compact, but again, they aesthetically don't look good. We also started to find growers that were growing other plants that were also developing this purple coloration. So, about that, we have begonias, as well as lantana, and even mint that were developing this purpling during the first 5 to 10 days in propagation. So the objectives of our study were really to determine if cuttings placed under LEDs developed any sort of nutrient deficiency, right? We wanted to make sure that what was causing this purple and purpling and chlorosis. We also wanted to determine if the foliage pigmentation was caused by an accumulation of anthocyanins. Now, anthocyanins are the blue, purple, and red pigments that we find in foliage, as well as in flowers. They're really what give us those attractive colors that allow us to sell plants. But most importantly, we wanted to determine how we could prevent these undesirable foliage pigmentation, because again, so many growers have switched to utilizing LEDs. So what we did is we worked with Ball Horticultural Company as well as Signify to work on this study. And we used 3 different petunia cultivars within one series. So we looked at the Sure Shot dark red, dark blue, and dark white. And again, we focused on petunia because it was the #1 species that growers were reporting issues with. And again, it's a very important species that's grown by many growers. We wanted to maintain a daily light integral in the greenhouse of 10 to 12 mils because our previous research had shown that this is the daily light integral that you want to achieve during rooting. As I mentioned before, maintaining a vapor pressure deficit of 0.3 kilopascals is quite important, especially during stick. And after stick, we want to increase that vapor pressure deficit gradually. In our mist, we provided 60 parts per million nitrogen. And one really important thing, we maintained our mist temperature at 70 degrees. Now, here's where the study begins to get complicated. We had two different greenhouse compartments. One where the air temperature was relatively cool. During the day, we maintained 72 degrees for 16 hours and 66 degrees for 8 hours, which gave us an average daily temperature of 70. Or we maintained 75 degrees for 16 hours and then 70 degrees for 8 hours, which gave us an average daily temperature of 73. We then placed those trays of cuttings either on a bench with no root zone heating, so a root zone temperature of 70, or with root zone heating at a temperature of 76. We also had a calcine treatment. And during this calcine treatment, we had basically 50% shade over those cuttings so that they weren't receiving high intensity of light from the LEDs, which again, we're providing 120 micromoles as needed. But again, we were providing a 16-hour photo. And what we wanted to do is, again, we had never heard of these symptoms under high pressure sodium lamps. So that was kind of our control. And we looked at two different LED fixtures, one that had a low percentage of blue light, so that's what this LB stands for, and another fixture that had a medium percentage of blue. So what we're looking at here is that light quality that we are receiving from the various fixtures. So remember, 400 to 700 nanometers is that photosynthetically active radiation. And we can see that our high pressure sodium lamp, right, we have a little bit of light output in the blue region. We have a little peak here. And then we have quite a bit in the red, and we have a little bit more in the far red. Now with our LEDs, you can see that we have a peak in the blue and we have a peak in the red. And slight differences between our low blue and our medium blue fixture in terms of, see that blue output. Okay, so again, this is a very large study where we had 24 treatments. So here's just showing you, right? We had one greenhouse that was our warm average daily temperature and then our slightly cooler. And then we had our three different fixtures. We had either no root zone heating or root zone heating, and we had either calcine or no calcine. So again, just to kind of show you, these are our structures, right, where we're providing the calcine. Here's our different benches providing either root zone or no root zone heating, and then our various light levels. And again, here's our various, our three different cultivars, where you can see that some cultivars began to show the purpling quite early, others did not. So now let's go through the results. What we are seeing here is cuttings that were rooted after 16 days under LEDs providing deep red, white, low blue. And again, this is a daily light interval of 10 moles of light. This was our coolest air temperature and no root zone heating. So again, cool air, cool root zone temperature. Here, for the first 6 days, we had shade cloth over the cuttings and no shade cloth. So again, we are definitely seeing that purpling. Maybe it's slightly less when we had shade cloth for the first 6 days, but again, still relatively low quality liners. Now here, we increased that air temperature. Excuse me, we had a cool air temperature, but we had root zone heating. So we increased that root zone temperature by 7 degrees Fahrenheit. Under that calcine treatment, we can see that, again, we're starting to see a lot more green foliage. Here and there, we'll have some of that purpling. But when we didn't have that shading during this first 6 days, we had a little bit more purpling. Now what happens when we increase that air temperature by 3 degrees, right? We went from 70 to 73, but here we are not providing root zone heating. So again, under that calcine, cuttings are much greener. little bit of purpling. And then here, again, much greener under no shade with a little bit of chlorosis here and there. Now what happens when we increase both the air and the root zone temperature? Again, this is still under that low blue. Well, we definitely under the shade have much greener foliage, right? But when we don't provide shade, we do see a little bit of purpling. One other thing that you may not have noticed is because we provided shade for 6 days, our leaves are slightly larger, right? That's not due to photosynthesis. It's mainly because the plants were under a slightly reduced daily light interval because of the shade. Now, let's look at the cuttings under our medium blue LED treatments. Well, because we're providing slightly more blue as we would expect, we saw a lot more purpling, especially when we didn't provide that calcium treatment. Again, this is cool air, cool root zone. Now what happens when we increase that root zone temperature by 7 degrees? Well, as we saw earlier under the low blue treatment, a lot greener. Here and there, we'll see some yellow, chlorosis or purpling, and slightly more when we don't have that calcium treatment. What happens when we increase the air temperature, but do not provide root zone heating? Well, here, actually, the plants are not nearly as green. We do have some purpling, as well as under no shade. What happens when we increase both the air temperature and the root zone temperature? Well, under calcine, look at how nice and green these cuttings are. And even under the no calcine, and again, here you see the large difference in leaf size again, because we've reduced daily light interval for the first 6 days, we see larger leaves. What about the nutrients? Well, we found that the highest concentrations of NPK, nitrogen, phosphorus, potassium, as well as calcium and magnesium were under the treatments that were basically under the high pressure sodium lamps and a warm air temperature and a warm root zone temperature. And we found that we had the highest concentrations of iron and sodium when we did not provide a calcium treatment and we had a slightly cooler air temperature. Now, which treatments had the lowest concentration of both the macro and the micronutrients? Well, it was under the deep red, white, medium blue LEDs, a cool air temperature, and a cool root zone temperature. So again, no root zone heating. Our second lowest concentration of macronutrients is again with the low blue, cool air temperature, and cool root zone. And then the lowest micronutrients were under these treatments. So again, this is showing us that again, there is some nutrient deficiencies going on when we have cooler air temperatures and cooler root zone temperatures. So again, this is just showing us an example of our cuttings grown under a high pressure sodium lamp at the warmest air temperature and the warmest root zone, where again, we see what we would expect, a nice green liner, no nutrient deficiencies. But here we have the example where we have our coolest air and root zone temperatures under low blue LEDs and medium blue LEDs. So you can see that under the medium blue, we have a lot more purple, right? So what's occurring here? Well, because we're pushing those plants so much with such high light intensities of 120 micromoles, right? Those plants are depleting the nutrients, that little bit of nutrient charge that was in the substrate, as well as the fertility we're giving them, as well as those cooler temperatures, right, in the root zone, as well as the air temperature, are not allowing those nutrients to move as quickly. And we're seeing some of that chlorosis in the form of phosphorus deficiency. When we look at the anthocyanin content, again, this is the what's going to give us those pigment colors, especially the purpling. Here we have, and they go, this is a complicated figure, but here's our cool air temperature. Here's our warm air temperature. These figures here are the high pressure sodium. These are our low blue LEDs. These are our medium blue LEDs. And here we have our root zone heating, calcium treatment, root zone heating, no calcium treatment, no root zone heating, calcium, and then no root zone heating and no calcium. So what we find is that under our LEDs at the coolest air temperatures, when we didn't provide any root zone heating, we had the highest concentrations of anthocyanin. So again, those purple pigments were being expressed much more heavily under those cooler air temperatures and no root zone. Where when we looked at the warmer air temperatures, really we saw very little differences, right, between the HPS, the low blue, and the medium blue LEDs. So again, a lot of information here, but again, it's telling us what we were visually seeing. So what are the take-home messages thus far? Well, temperature seems to play the most influential part in preventing these foliage purpling, right, under LEDs. If we reduce the light intensity for the first 5 to 6 days, that can also be beneficial. But some of the challenges with these two methods are not all growers have root zone heating, as well as many growers say, well, I switched from high pressure sodium to LEDs because of the energy savings, but now you're telling me that I need to increase my air temperature or provide root zone heating. And again, you're still going to have energy savings, right? Because it's much more energy efficient to heat a greenhouse with natural gas or propane than it is with a high pressure sodium. But this is going to be a little more challenging, right? I'm telling you that you need to add shade under your LEDs to reduce that light intensity, right? And it's kind of counterintuitive. There is a way to dim the LEDs that would be beneficial, or to start the cuttings in an area where you have a lower light intensity and then move them to an area with higher light intensity after those first 5 to 6 days. That could potentially do it. So the recommendation for propagators using LEDs, again, warmer air temperatures is probably going to be the most practical way of offsetting and preventing this purpling, or providing root zone temperatures, right? If you have a root zone heating system, use it. Probably less practical, as I said before, is reducing that daily light interval during callus formation. You could do this by using some sort of shade tent, dimming your LEDs if you have that capability, or starting the cuttings off in a separate area and then moving them out. So as I mentioned before, there's definitely future work that needs to be addressed, and we've put in some grants that hopefully will get funded to help us further investigate in this area. We need to see if there are other species such as Calibrachoa, as well as begonias, if they are going to have similar results as to what we've seen with petunia, with increasing the air as well as the root zone temperature. We also want to determine, does this purpling occur under other LED fixtures, primarily those that emit white light, right? So there's more and more we're seeing LED fixtures that, again, just provide white light. We want to also try to determine if providing far red light will eliminate or reduce the purpling. And the reasoning is that HPS fixtures provide far red light, and we don't see the purpling under high pressure sodium lamps. And lastly, one thing that we would like to work on is to determine if we provide a little bit of an additional phosphorus to the mist or the feed, can that potentially alleviate the purpling? That would probably be one of the easiest things for a greenhouse grower, right? Is just to adjust their fertility. So again, these are things that we hope to look at in the future when it comes to this research. Again, here are some resources that we have here at Michigan State. If you go to our website, if you're interested in light, we have lots and lots of articles under this tab called Light Management in Controlled Environments, as well as articles on propagation of plugs and liners. We recently, in the November issue of Grower Talks, had an article which explains some of the work that we've done in this area. So if you'd like to take a look at that. And then we'd like to thank our sponsors for this research, which were Phillips Signify, the Floriculture Nursery and Research Initiative, Ball Horticultural, as well as the MSU Ag Bio Research. We'd like to also thank our sponsors for today's webinar, which are Smithers Oasis. And I'd like to mention that the next webinar in the Grow Pro webinar series is Integrated Control of Thrifts with Dr. Rose Bernheis from Vineland Horticultural, and that will be on Tuesday, August 20th at 1 p.m. Eastern Time. Thank you very much, and I'm now available to take any questions that you may have.
Dr. Lopez, thank you so much for the great presentation. And now I would like to open up the session for Q&A. I know, Dr. Lopez, you mentioned that you're here.
Yes.
So let's see if we have any questions in the chat. I will read them out loud for you. And then we'll check the Q&A. Okay, we'll give some time to the audience. Meanwhile, I can ask you one question. So do all petunia cultivars, they turn purple under LEDs?
That's a great question. From what we have seen and heard from growers, no, not all of them. It typically tends to be petunia cultivars that have flowers that are darker in color. So those that are purple, sometimes the blue or even the red flowers. And why that occurs, we don't really know. So yeah, great question.
Actually, I have done my PhD in roses in flower color, and I tested different anthocyanin pigments. So for me, I worked on a flower color that changed color from yellow to pink, and it turned out that there was a specific anthocyanin pigment that was related to the flower color change. So I was just wondering if you tested any specific anthocyanin pigments, or was it just the total anthocyanin content?
Yes, we just tested the total anthocyanin content.
Mm-hmm. We have one question here. So Mary is asking, can you address the cost difference between adjustable and non-adjustable LED fixtures?
Okay, so I won't be able to give you, the exact numbers, but we'll be able to tell you that, yes, when you have a LED fixture that is adjustable, you're definitely going to be paying, right, for that capability. And those fixtures that are adjustable, we typically find that not a lot of growers will install that type, mainly because those are used more for research. It can be challenging for growers, to know like what particular light recipe do you need to use, right? Do you need, there's a lot of different combinations. And so, that's why we don't necessarily see growers using them. But again, there's that obviously that added cost.
Thank you for answering that question. And audience, please feel free to ask any more questions. And I can ask you one more question. So should I provide fertility during cutting rootings?
Yes, so one thing that we recommend, regardless of the species, is that you should provide fertility in the mist. Probably the only exception would be poinsettias, where phosphorus can cause the apical meristem or the growing point to desiccate, or sometimes you'll get what's referred to as epinasty, where those shoot tips tend to twist. But again, with most other species, yes, you do want to provide fertility, because you got to think about, right, that cutting was harvested from the stock plant, and from that time point until it's in propagation, it is losing those carbohydrates as well as the fertility, and so we want to provide that through the mist.
Thank you. And we have another question in the chat. Is there any temperature difference between day and night?
Yes, so we did have a warmer day and a cooler night in both the scenarios that we utilized, because obviously that's what most growers will do. And in our first scenario, we had, I believe it was 72-66. So definitely a cooler night, which gave us an average daily temperature of 70 degrees. And then in our other compartment, we had an average daily temperature of 73 degrees Fahrenheit.
And then Jan is asking, can it be that the temperature drop from day to night is too fast?
Well, you know, we obviously were able to replicate what growers are seeing, right? And you know, growers propagating under a wide range of day and night temperatures. And so what we found is that when you have cooler air temperatures in the greenhouse, right, we want to try to have energy savings. This is when we saw the most intense purpling. And you got to think, right, as I mentioned during the webinar, plant temperature is about anywhere from 2 to maybe 4 degrees warmer under LEDs. So that, even though it may not seem like a lot, excuse me, under high pressure sodium, but under LEDs, you know, they're 2 to 4 degrees cooler. And so just that change in temperature could be what's causing the that accumulation of anthocyanins and the purpling that we're seeing. Obviously, we were able to alleviate that when we either increase the air temperature or we increase the root zone temperature.
We have another question in the chat. If I have delayed geraniums in transit and stick them later, would you recommend to reduce the amount of LEDs to reduce yellowing, purpling, breakdown, etc.? I'm doing feed in the mist on the poinsettia with no phosphorus. I think that's a separate question.
Okay, yeah. So for the first question, the yellowing that you see in geraniums is very different than what we're talking about here. That yellowing is primarily due to ethylene, right? During the shipping process, especially when there's extended shipping, we'll see ethylene accumulate within that box, as well as extreme temperatures, right? So if the box, the temperature gets pretty warm, there is increased respiration, which then leads to the yellowing that we often see with geraniums and prop. So one thing that I would definitely recommend, if you know, and a lot of folks ask, well, should I do this every time or only if I know if the shipment has been delayed? And we've done work with use of fascination, where you or fresco. And what you do is you basically apply that the day after you've stuck the cuttings. And what happens is you reduce that lower leaf yellowing and senescence. But one really important thing to note is that you have to use a rooting hormone, because again, you're allocating those resources within that cutting. And if you use either of those two products, you may have reduced or delayed rooting. So I can give you some articles of some of the work that we've done with fascination or fresco. In terms of the lighting, again, that's really not going to impact the yellowing too much. But again, if those cuttings are really wilted, you're going to want to reduce the light intensity for those first few days to you know, make sure that you don't have increased yellowing, or even just to help them gain turgidity.
And then we have another question by Mary. If you are applying fertilizer in the mist and I already have problems with high alkalinity, how is the residue buildup on the tissue addressed?
Great question. So the use of fertility in the mist is not necessarily going to affect the residue on the leaves. It's more, as you indicated, the alkalinity. So if you are able to you know, acid inject to bring down your alkalinity, that will definitely help with the residue. Even better, if you have the ability to use reverse osmosis water, that will, you know, really reduce your alkalinity. So it's not necessarily the fertility that is causing the residue. It's more so the the bicarbonates in that water that are leaving those white spots on the leaves.
So we have another question from Colin. When you say to utilize fertility on uprooted cuttings, is this prior to or after callus or root stimulation?
Great question. So we basically we start providing fertility from day one. And while you may think that that's a waste of resources, you got to think, what's our main goal with mist? It's really to keep that cutting turgid, right? We are not wanting to have water underneath that tray. If you are applying that much water in propagation, then that's too much. So really what we're doing during those first few days is trying to maintain those cuttings as turgid as possible until they form callus and then roots. And so we are basically foliar feeding, right? Providing nutrients to that cutting that has already depleted its carbohydrates and even some of those nutrients during transit. Once they develop roots, then you need to obviously reduce your mist and provide fertility through overhead irrigation or what other method that you use.
Thank you. And let me see if we have any more questions. Okay, we have one more. Have you done trials with more species using feed in the mist to avoid purpling? I know geraniums, lobularia, herbs don't like feed in the mist.
So yes, we have done lots of studies where we provide fertility in the mist. And as I mentioned before, poinsettias are really the only ones that we have found that you have to be careful with. Is who was it that mentioned it earlier? Robert. With the poinsettias, and really it's the phosphorus that you need to be careful with. We've rooted lots and lots of herbs and never have had an issue. As I indicated before during the webinar, when it comes to the purpling issue, one thing that we would like to do in the future is look at fertility, right? Is there because we saw that phosphorus is one of the issues, right? That we have phosphorus deficiencies in those cuttings growing under LEDs. What happens if we add a little bit more phosphorus? Can we prevent that purpling that way without having to increase the air temperature or the root zone temperature? Another thing that we also want to look at is the lack of far red light, right? With the high pressure sodium, we provide blue light, we provide green, red, and far red. But with the LEDs, we are primarily only providing red and blue and very little to no far red. So is it that lack of far red that's causing this? Or is it that over the years, growers have provided just a higher and higher light intensity, right? Our recommendations when we started doing this research was around 70 to 80 micromoles. Growers are now lighting all the way up to 150 micromoles. So there's still a lot that needs to be done to figure out what other things growers can do to prevent these purpling and chlorosis issues that have recently developed.
Thank you. And I think we still have time for one or two questions. Please feel free to type any questions you have in the chat or in the Q&A. If not, then I would like to thank you, all of you, for joining us today for another session of AFE's Grow Pro webinar series. Join us next month for Dr. Rhodes Boytenhouse presentation on integrated control of thrips on Tuesday, August 20th at 1 p.m. Eastern Standard Time. You can register at endowment.org/growpro. While there, check out our past webinar recordings, other grow-related resources, and research reports available to you for free, and thanks to the industry support. We also want to remind you that research funding is available through AFE. The deadline to submit research proposal is this Thursday, August 1st. The link to submit proposals will be in the chat. If you have a project that solves scientific challenges the floral industry faces, we encourage you to apply. We ask you that please complete the brief survey about today's session, where you can suggest additional topics and help us continue to improve these webinars. Thank you so much for joining again, and have a great day.